Well, hello. I'm sure you've totally missed hearing my voice and watching these videos just as much as I've missed giving them since yesterday. So, fun world we live in, isn't it? All right, so today we're going to continue talking about exponential equations. We're going to really take a closer look at exponential growth versus exponential decay, and we're going to try to focus a little more on realistic situations. So we're going to keep our B number as a positive. We're not going to put that extra negative out front. So we're going to kind of be working a little bit more with, again, realistic equations, ones that we can see in the real world. All right, so on the left-hand side, we're going to talk about exponential growth. And what I'm hoping that you see is that we're always going to do everything in a left to right direction. We always want to count from left to right. So that's why it's called growth, because from left to right, you can see that we are moving in an upward direction as we follow through. Now, the equation, what makes it special, how we can know it's exponential growth without seeing a graph, is if that B number is greater than 1. Now, if you remember yesterday, we talked about how that B number cannot be exactly 1. If it is, and I actually just get a flat line across the graph, there is no curve to it. So if B is greater than 1, that means 1.00001 and higher and all that, we're going to get this exponential growth. There's a couple of examples there. Y equals 2 to the power of x, or y equals 7.5 to the power of x. Again, if those numbers are bigger than 1 that's out in front of there, we're going to get exponential growth. Now on the right-hand side, exponential decay, you can see in the graph, again, if you're going from left to right, we always do left to right when we describe graphs, you can see that the graph is dropping down. That's what we call decay. And if you're not really sure what decay means, don't worry about it. We are going to talk a little bit about decay and talk about how we use that particular math feature to tell how old something is. It's called dating, carbon dating usually. So again, that'll be actually a lesson we do down the road after we're a little bit more familiar with these graphs. All right, now what's special about this particular equation is it looks the same, except that B number is going to be some number between 0 and 1. Now, if it was actually equal to 0, then we wouldn't really have an equation. If you make that B number 0, 0 to any power is just going to give you 0. So we'd have another flat line. Same with the thing you'd happen at 1. So we're talking about B being essentially a fraction or a decimal somewhere between 0 and 1, but not equal to 0 and not equal to 1. So there's some examples down below in green. Y equals 0.5x. Again, 0.5 is between 0 and 1. Or y equals 3/4 x. Again, 3/4 is being somewhere between 0 and 1. All right, so second part of our lesson today is we're going to talk about what's called domain and range. The first domain, it's a set of all possible x values in a function. And it's going to be the same answer for every one of our problems this chapter. So it's all reals for all exponential functions, because we can essentially put whatever dang well number we want in that spot. It doesn't matter. I can put negatives there, fractions there, zeros there, ones there, positives there. It makes absolutely no difference at all what number I put there. Now, the answer I get out the other side, that could change. Now, if you're tired of typing the word all reals, there is a symbol for it, but I haven't seen it on any of our computers. The symbol for all real numbers is this double stick on an R. So it's like a capital R with two sticks on the left-hand side. That stands for all real numbers if you're a person who's writing with your finger or a stylus. But if you're typing, there isn't ever a symbol I can find for that. So I just have to write the word all reals. Right, now range is the opposite. It's the set of possible y values for a function. That's your up and down numbers. And if you remember what these graphs look like, we have these horizontal asymptotes where the graph starts to flatten out. Now, normally towards 0 is where it flattens out. So what we're looking for our range is it's all real numbers, but it's always above or below. And again, because we're going to be doing things that are more realistic, we're going to be viewing mostly above and not so much the belows, but belows are possible. Above or below the horizontal asymptote. So we get horizontal asymptotes when we start adding in an extra number in the back here. That's our horizontal asymptote number. It tells us where our graph's going to flatten out at. Now, if we don't have that number, like this equation here, there is no plus or minus number in the back, then that just means it's a 0. Like I said before, that's kind of the normal place for these to have horizontal asymptotes. But if there's a plus or minus number after that exponent part, then that will be where the horizontal asymptote is. So let's take a look at some examples. All right, so let's look at this line in blue first. And in case you can't see, here's my x-axis and my y-axis. So that line in blue, the domain, is going to be those all reals. All real numbers. You can put any number in for x. The graph can go left or right. There are no holes or vertical asymptotes here. But there are horizontal asymptotes, and you can see it right here for the blue one. So where is it? Well, it happens to be at positive 3. And you can see in the equation right here where we can see that. We see that plus 3 in the back, so our range would be all reals, except there's an exception. All right? All reals, except the y has to be greater than 3. It's above the horizontal asymptote. Not equal to it, so no equal to 3, but greater than 3. Now, let's take a look at the next one. The orange one in the middle there. All right? The domain, once again, is all reals. I'm going to use the symbol because I'm kind of running out of space here. And then the range. It's going to be all reals, all right, with its exceptions. All reals where y is greater than what number? Well, the horizontal asymptote on that orange one looks to be the x-axis, or 0. So all reals where y is greater than 0 numbers, or greater than 0, means, again, horizontal asymptote at 0. Now the red one, actually, before I go on, you can see that there was no number in the back of that equation. That's where we get the 0 from. All right, now the red one, the domain, again, exponential, so all reals. Then the range is all real numbers, but there's, again, some exceptions. We have to be greater than, well, in this case, that number would be negative 3. That's where we're at on the graph. That's where the horizontal asymptote is. So, again, we're talking about all real numbers, so fractions, decimals, all those things are fine, as long as it's greater than negative 3, nothing less. But everything up above. All right, I hope this makes sense. This is what your work is today, is looking at some graphs and deciding, first off, if they're growth or decay, and then secondly, looking at the domain and the range of these graphs. All right, good luck.